with machine learning, deep learning, you should at least go through all these examples, keras.io examples. So today we will go through structured data set. So structured data set is nothing but it's like the tabular data set which is having some kind of structure, like as a table or as an image. So we saw in our discussion of graph neural networks that graphs can be applied to unstructured data as well. But this is for structured data analysis. And so, okay, so this is an example which demonstrates how to do structured data classification. Starting from a raw CSV file, our data includes both numerical and categorical features. So I will open this in Colab, otherwise it's difficult. Yeah, so the data set is provided by Cleveland Clinic Foundation for Heart Disease, and it's a CSV file with 303 rows. Each row contains information about a patient uh, who is basically a sample, and each column describes an attribute of the patient. We use the features to predict whether a patient has heart disease or not. So that is the problem, and this is the target variable. That is whether the patient has got heart disease or not. So one is corresponding to true, and zero represents false. And these are the columns in the data set which are available. So these we'll use as the predictors. So what is the age, sex, chest pain type 0, 1, 2, 3, 4? What is the resting blood pressure, the serum cholesterol, fasting blood sugar, resting electrocardiogram results, maximum heart rate achieved, and exercise-induced angina, ST depression induced by exercise relative to rest. So these are the different variables that we will use. Now you can see that we are importing TensorFlow and NumPy pandas. Okay, so this is running, and this code is basically you are reading the pandas data frame, the CSV file using pd dot read underscore CSV. And the dataset includes 303 samples with 14 columns per sample. So 13 features plus the target label. So let us see the shape of the dataset. We can see 303 samples and 14 columns per sample. So this is the preview of the first few samples. So you can see that these are the variables, and we have what we want to predict is whether the person has got heart disease or not. And the last column target indicates whether the person has heart disease or not. And so we will sample from this data frame. We will divide it into the validation data frame and train data frame. So we will first select the 20% data from this data frame. So using this function sample, which you can use over pandas, any pandas data frame. And and uh, for reproducibility, you use this random state equal to 1337. And then from the training data, you construct in a way that you would basically drop the validation data frame from the trained data frame. So let us see how much data. So we have 61 samples for validation and 242 samples for the training. And let us generate tf.data.dataset objects. So we are creating this TensorFlow data type data. And so what this function is doing is data frame to data set. It takes in as input the pandas data frame, and you basically make a copy of this first, because so this is actually a very good programming paradigm if you are working with pandas, and you do not want your original data frame to change, because if you will do some operations on the data frame and you will just think that you are saying maybe something equal to data frame, that doesn't create a copy of that. It just what it would just do is create a pointer to the original data frame, and whatever you will change to the new data frame, that those changes would be reflected in the original data frame. So now this becomes a local copy of this function, and it would not affect any change in the original data. So labels equal to data frame dot pop target. So what this will do is this will extract target and just put in labels, and also remove the target variable from this data frame. So after that, you can, so this function tf dot data dot from tf dot data dot dataset, this is the dataset class. This has got the function from tensor slices. So from tensor slices, and this is the data frame. This is the input data set, which does not contain this target now. And so this is okay. So this is the x variable, and this is the y, that is the target, and ds equal to ds dot shuffle buffer size equal to so length of data frame. So this will actually effectively shuffle the data set, uh, so as to help you generalize it. Now you can see that this is the train ds, which will be tf dot data tf tensorflow data type, and validation ds. So you just pass this train data frame and val data frame to this. And now let us see. Okay. So what has this done? So you can just print train underscore ds here, and you can see that it is a shuffled dataset element spec with these inputs: age, sex, and resting blood pressure and all as inputs, and the target is your this labels, these labels. So each dataset yields a tuple input comma target, where input is a dictionary of features and target is the value 0 or 1. So you can just print a particular so you can just extract one sample from the training data frame. You can say for x comma y in train ds dot take one, and then print, so what is x and what is y. So this is your y, this is your target, and this is your this is your input. Okay. Now let's batch the datasets. So batch basically means that you will it, it you are extracting this many number of samples from the dataset. So train underscore ds ds, you can see now it okay, we will see by this. Yeah. So you just, if you just take one now, that will extract a batch size of 32. So you can see this. So this has extracted a batch size of 32 for so this was our, these were our variables, right? So this has extracted this batch size. So these are the, this is your, these are your inputs, and this is your, this is your target. So yeah, it has So you can see that this is the okay. So this is the first variable, which is age, and then this is sex. So these are, you can see 32 values here. Okay, for the first variable, and then for the second variable, and then going up to this variable, which is text, this thal. What was thal? Uh, this categorical. So 3 is equal to normal, 6 equal to fixed defect, 7 equal to reversible defect, and then this is your target. Target is whether the person has got a heart disease or not. Now we will do some feature pre-processing with Keras layers. So the following features are categorical features encoded as integers. That is, all these features are categorical features, and we will encode these features using one hot encoding. And we have two options here. So the first is category encoding. So category encoding requires knowing the range of input values, and will error on input outside the range. So outside the range, if you have any value, it will give you some kind of error. Otherwise, it requires the knowledge of the range of input values. And integer lookup will build a lookup table for inputs and reserve an output index for unknown input values. So whatever unknown input values are there, uh, it will just reserve a particular class for that. We'll see how to do this. And for example, we want a simple solution that will handle out of range inputs at inference. So we will use integer lookup, and we also have a categorical feature encoded as a string thal. We will create an index of all possible features and encode output using string lookup layer. So finally, the following feature are continuous numerical features. So these features are numerical, and for each of these features, we will use a normalization layer to make sure that the mean of each feature is 0 and standard deviation is 1. And below we define 3 utility functions to do these operations. So encode numerical features to apply feature-wise normalization, encode string categorical features to first turn string inputs to integer indices, and then do one hot encoding, and then encode integer categorical features to one hot encode integer categorical features. So we'll see this. So these are three layers which are available, in fact, inside Keras. So you can see integer lookup, normalization, and string lookup. So here, this function encode numerical features. This is taking the in as input the name of the feature. So okay, so the feature, the name, and the data set. So you are creating an object of this class normalization. This is the normalizer. And so what you will do is, so prepare a data set that yields only our feature. So this will just extract that the feature for you. And when you extract that feature, your dimension will reduce for the x. So it is this is changing the dimension accordingly. And then you say normalizer dot adapt, so feature ds. So this is for the numerical features. So this will create normalize the data set in such a way that your mean is 0 and standard your mean and standard deviation is 1. And then so once you perform this, so once you do this, so you say encoded feature equal to normalizer feature and return encoded feature. So we will see this, how this is working. Yeah, so you can see this is, for example, the age encoded as feature. Okay, so age is okay. We will see this later. or let us go through this first. So what you are creating is building a model. With this we can create an end-to-end model. So you are creating the Keras input data types. So these are your all your categorical features, and then you have this as a string uh, data type, the variable thal, and then we have these numerical features, right? So these are all our numerical features, and we create a list which is a list of all the inputs. So which is a mix of categorical features encoded as integers, categorical features encoded as strings, and also numerical features. So then we will first see how they are performing this age. So age encoded equal to encode numerical features, which takes in as input the Keras data type age, and then you pass on the name of this column inside of this corresponding variable, which is age, and the data frame, which is the train ds. So it will go inside this function, and what this will do is, so feature ds equal to dataset dot map lambda, so x comma y, such that, so this will just return from the from your data set. So this is the train underscore ds. So it will just yield, or it will just give you the uh, the age. So in this case, particular case, age, and feature ds equal to feature ds dot map lambda, so x, such that tf dot expand dims x comma minus 1. So this will just flatten that variable, and then we are saying normalized dot adapt feature ds, and encoded feature equal to so normalizer feature. So you can see there, this was the age input variable, and you first apply the normalization over over the numerical data, which is which is from this is actually a pandas data frame. And so but although it is converted to the tensorflow data, the feature ds, and this feature is actually this keras dot input shape one. So this is the age keras dot input data type. So that is what it is returning, a normalized keras dot input data type, and from this we get age. So similarly, we will see. So they are encoding this categorical features as well, which are, so the categorical features which are encoded as integers, right? So you first have the feature name, dataset, and the last is string. So they have basically, in this function, they have taken into consideration both the types of data sets, that is the categorical features encoded as integers, and categorical features which are encoded as string. So in the last argument, if you just pass false, so that basically means that it is not a string. So let us see for this first. And in this case, so just like numerical features, you pass the keras dot input data type, and then the name of the variable in the pandas data frame, and then the pandas data frame. So what this will do is, so this will say lookup class equal to string lookup, if string, so if string else integer lookup. So you will make this lookup class. So this will be either string lookup. So this is string, in this case is false. So we will get lookup class as integer lookup. And then we can say, so lookup equal to lookup class output mode equal to binary. So we are turning the categorical features into one hot encoding, and we are creating binary outputs of this data set. So this data set text. So this is we are converting into binary. So it's just having zeros and ones. And okay, so prepare a data set that yields only our features. So similar to the categorical features, we will just extract that feature, expand dims, just expand it, and then lookup dot adapt. So lookup is this lookup class, which is we are getting from this either if it is string lookup or an integer lookup. And then what we will do is we will put this lookup. So after adapting to this, we will so this feature, which is the keras dot input data type, we return a proper categorically encoded feature from this function. Now when your data type is a string, so we say true here. And when we say true here, so this lookup class will be string lookup. So we can just maybe see some more details of string lookup keras. So it says that this is a pre-processing layer which maps string features to integer indices, and this layer translates a set of binary strings into integer outputs via a table-based vocabulary lookup. And this layer will perform no splitting or transformation of input strings. For a layer that can split and tokenize natural language, you see text vectorization layer. So this is not performing text vectorization. And okay, so the vocabulary for the layer must be either supplied or on construction or learned via adapt. So that is what we are doing. We are using dot adapt, and we are learning the vocabulary for the layer. And during adapt, the layer will analyze a data set, determine the frequency of string tokens, and create a vocabulary from them. So if the vocabulary is capped in size, the most frequent tokens will be used to create the vocabulary, and others will be treated as out of vocabulary. So this one, what it will do is it will create the most frequent set of vocabulary as vocabulary. And so the layer will analyze the data set, determine the frequency of individual string tokens, and create a vocabulary from them. So only if it is capped in size, the most frequent tokens will be used. Otherwise, all the tokens will be used. And so there are two possible output modes for the layer. When output mode is int, so input strings are converted to their index in the vocabulary. And when output mode is multi-hot, count, or tf idf, so input strings are encoded into an array with where each dimension corresponds to an element in the vocabulary. So this is similar to so output mode is int. Basically, it will encode it as a string, that is 1, 2, 3, 4, 5. Whereas if it is multi-hot encoding or count or tf-idf, it will be like a vector, right? So 0, 0, 0, 0, 1, something like that. And the vocabulary can optionally contain a mask token as well as an out of vocabulary token. So you can pass an out of vocabulary token as well. And the position of these tokens in the vocabulary is fixed. So when the output mode is int, the vocabulary will begin with the mask token, and so followed by the OOV indices, which is the out of vocabulary indices. And when output mode is multi-hot, count, or TF-IDF, the vocabulary will begin with OOV indices, and instances of the mask token will be dropped. So these are the different arguments that you can pass. So this is the max number of tokens, number of out of vocabulary indices, the mask token. Okay, so yeah, so let's say you have a vocabulary as this. So this is a see, these are the this is, let's say, your entire comprehensive list of tokens which exist in your dictionary or vocabulary. Now this is your data set, data equal to tf dot constant. So this consists of two lists, a c d d z b, and then you say layer equal to tf dot keras dot layers dot string lookup, and vocabulary equal to vocab. So what this will do is, so you are saying, so okay, so you create this layer, and using this vocabulary vocab, and then you to this layer you pass this data, right? So this data consists of a c d, they are in the vocabulary, d again is in the vocabulary, z is not in the vocabulary, right? So you can see that here, here now a is given the integer index 1, c is given 3, so d is 2, d again is 2 here, and this z, this was not in the vocabulary, so this one has been assigned as a 0, right? So this is the out of vocabulary index, and here this was b, so b is assigned as 2, so it was 2 in the vocabulary. And creating a lookup layer with adapted vocabulary. So this example creates a lookup layer with lookup layer and generates the vocabulary by analyzing the data set. So you have this data tf dot constant act dzb, and you create a layer without a vocabulary. So you are not passing any vocabulary argument here, and then you say layer dot adapt data. Okay, so you just adapt this layer to this data, and then if you say layer dot get vocabulary, so all the unique tokens in the data, they are now a part of the vocabulary, and the first one, the unk, is the undefined. So note that the ov token unk has been added to the vocabulary. The remaining tokens are sorted by frequency, and so more they are occurring, the first they come, so d is coming twice, right? So it is coming first, and and then by inverse sort order. So then by, so first z c b a, so then so all of them are coming once, so they are coming as inward sort order, and okay. So the remaining tokens are sorted by frequency and then by yeah. So, so this is the one hot encoded output. So here you can see that you encode. So if you have this vocabulary, and you have this data, and you create a string lookup layer with vocabulary equal to vocab and output mode equal to one hot, and then you pass this data to the layer. So this will create a one hot encoded representation. So the so in this case, the first one is so this is, so the first letter is A, right? So it comes at the second position. The first one is always reserved for the unk, or the undefined, or a token which is not there in the vocabulary. So Z is not in the vocabulary. You can see that this corresponds to Z 10000. And now you can also create a multi-hot encoded output. So configure the layer with multi-hot encoded output, and so this is so in this one you see we have the vocabulary as A B C D, and you have the data A C D D D Z B Z, and you encode it as a multi-hot. So you create this multi-hot encoded layer, and then you pass the pass the data to the layer. So in this case, you have a as 0, so 0 1 0 1 1 1 0 1 0 1. So that is what basically creates your multi-hot encoded uh, output. And so TF-IDF. So this TF-IDF is a very important concept that you should know about. It's inverse distributed frequency, something like that. And so this is basically inverse normalization by the frequency in which a particular token is being represented in the data. So it will normalize it according to that. Okay, we have seen string lookup, and okay, so we'll just have a brief look at integer lookup layer, categorical feature processing layers, and we have the integer lookup layer. So this is so this is also a pre-processing layer which maps integer features to continuous ranges, and this layer maps a set of arbitrary integer output tokens into indexed integer output via table-based vocabulary lookup. The layer's output indices will be contiguously arranged up to the maximum vocab size, even if the input tokens are non-continuous or unbounded. And the layer supports multiple options for encoding the output via output mode. So the output mode and has support for out of vocabulary tokens and masking. So the vocabulary for the layer must be either supplied on construction or learned via adapt. So again, here is similar to the string lookup in this sense. So we'll see the examples. So let's say your vocabulary is 12, 36, 1138, 42, and this is your TF TensorFlow data. So TF dot constant 12, 1138, 42, 42,036. You create this layer TF dot keras dot layers dot keras dot integer lookup, and you pass this as the vocabulary argument you pass as vocab. So the data that like the encoded data that you will get is this. So the first one is reserved for the unk or the number which is not there in the vocabulary, and otherwise you get, so this is the first number, right? And then 1138, so 1138 is 123 at the third position. Then you have 42, 42 is at the fourth position. Again you have 42, 42 is at the fourth position. Then you have 1000, 1000 is not there in the vocabulary. And then you have 36, so 36 is at the second position. Okay, so these are the these are the salient features of integer lookup and string lookup. So this is the lookup class that you will define, and so this corresponds to the pre-processing after applying these functions. So your pre-processing is now over, and you then can we'll concatenate all these layers together. So this will turn into all features. So all features equal to layers dot concatenate. So all these encoded features you can see we are concatenating. Yeah, and then we will create a neural network from here. So you can see layers dot dense. So the first layer will consist of 32 nodes, and it will take in as input this all features. This will perform linear combination and a nonlinear activation with the activation function as ReLU. And then we have a dropout layer with 50% dropout rate, and then we have the output. So output equal to layers dot dense. 1 comma activation sigmoid, and this will take in as input this x, and we'll create the model like this now. So model equal to keras dot model all inputs. So we have all inputs as input to the model, and with those all inputs, uh, they will go, and we will have the output as the target. So with the all inputs as input, the how the output will be created is, you can see, you can go in an inverse manner, and uh, the from the all inputs. So the all inputs has this all these inputs. So we you can see that you can create the neural network graphs in a reverse manner. So with all these all these encoded variables, they are built on these variables from the inputs, and then from these encoded variables, this all features is made, and from all features you can see we get x here, and then x, from x again we get x, and then we get the output. So that's how you can see the model is being defined here. And then you say model dot compile, what is the optimizer that we are using? The Adam optimizer, the uh, the loss function, which is the binary cross entropy loss, and the metrics, which is accuracy. So encode categorical feature is not defined. We did not run this. Okay. So now let us visualize our connectivity graph. So you can use this function plot model, which is defined in the class utils from Keras, and you can just pass your model, and you can give different arguments like show shapes equal to true, uh, rank dir equal to lr, and this will visualize your connectivity graph. So you can see here from this one that you have these inputs. So you have this variable sex, CP, FBS, resting ECG, and all these variables which are getting converted to, which are then getting encoded. So these are the encoded variables, right? So you have string lookup for the string variable, integer lookup for the integer variable, categorical integer variables, and then you have normalization uh, for the variables which are numbers. You concatenate, basically concatenate all of them. So this turns out to 36 uh, uh, input variables, and then you pass it to a dense layer, a dropout, and a dense layer of size 1. So this is your connectivity graph, and then we will train this model. So let us see what is the accuracy that we are getting on the. So you can see here, while training, we give this as the train data set, and so this is our val ds is the validation uh, data set for us. So okay, we have already defined the val ds uh, before. Where did we define val ds? Yeah. So here we have defined the train DS and val DS with their respective batch sizes as well, and then we are creating these the keras dot input uh, data type from train DS, and so then you can see that we quickly get to an accuracy of around 80%. Okay. So inference on new data. So to get a prediction from a new sample, you can simply call model.predict. there are just two things you need to do: wrap scalars into a list so as to have batch dimension and convert to tensor on each feature. So you can see this. This is the sample that we have. So age is 60. You have these categorical features, and you have these numerical features, and you have this string categorical feature. So then you create an input dictionary. You just say name is the key, and the value is convert to tensor. So this is the value that we are converting. And for name comma value in sample dot items. So it will iterate over this sample dictionary, and it will create this input dictionary, and then you can just say model.predict input dictionary. So this model inside it will do all those encodings and whatever we pre-processing we have done. So this gives you that the particular patient has a 23.4% probability of having heart disease as evaluated by our model. So this is an end-to-end example on the structured data set that we have seen. Okay. So then we will okay. Next 10:51, and okay. So we will see maybe spinning up .openai where we left yesterday, the deep reinforcement learning part, and with that maybe we can class. Okay. So we were here yesterday, key concepts in RL. So what can RL do? And we have seen all this theory, the rewards, the actions, the state variables. Are there any questions on the structured data set, structured data example that we saw today? Uh, this example. So we saw that for a reinforcement learning framework, we have this entire framework wherein you have the agent takes an action 80, then you have an environment, then you have the state and the reward. So we ended at Bellman equations, and we saw uh, how to construct the four equations: the on policy value function, the on policy action value function, and the optimal value function, the optimal action value function. So yeah, this one we did not see. So for those of you who are new to this term known as the Markov uh, Markov property or the Markov decision process. So wherever you encounter the terminology Markov, you should understand it from this. Like this is the this is the bottom line of the Markov theory, that the transitions depend on the most recent state, and in the case of reinforcement learning action, and no prior history. So if you are simulating something with a Markov decision process, or anywhere where you encounter terms like Markov chain or Markov anything related to Markov, that basically means that you're if you are talking about time, so at the next time step only depends upon the previous time step and not anything beyond that. So that's about Markov. And so there are different types of reinforcement learning algorithms, and we will see here taxonomy to these algorithms and a list to algorithms in the taxonomy. So now that we have gone through the basics of reinforcement learning terminology and notation. We can cover a little bit of the richer material, the landscape of the algorithms in modern reinforcement learning, and a description of the kinds of trade-offs that go into algorithm design. So this is the taxonomy of reinforcement learning algorithms. You have model-free algorithms and model-based algorithms. Model-free algorithms can be classified into two types. One is the policy optimization, and another is Q learning. So in policy optimization, you have policy gradient, A to C, A to A3C is actor to critic. Then PPO is proximal policy optimization. Then you have TRPO, DDPG, TD3, SSC, and so these come under policy optimization, and they also come under Q learning. So then you have the most simplest Q learning algorithm is the deep Q networks. We'll see these algorithms, and then we have model based algorithms. So either we have been given a model, for example alpha 0, or we have to learn the model like world models, I2A, MBMF, MBV. So we will start this section with a so they say that with a disclaimer. It's really quite hard to draw an accurate, all-encompassing taxonomy of the algorithms in the modern RL space, because the modularity of algorithms is not well represented by the tree structure. Also, to make something that fits on a page and is reasonably digestible in an introductory essay, we have to omit quite a bit of more advanced material like exploration, transfer learning, meta learning, etc. And that said, our goals here are to highlight the most foundational design choices in deep RL algorithms about what to learn and how to learn it, to expose the trade offs in these choices, and to place a few prominent modern algorithms into context with respect to those choices. So, what is the difference between model free and model based RL? One of the most important branching points in a reinforcement learning algorithm is the question of whether the agent has access to or learns a model of the environment. Whether you are trying to model the environment or not, the that is a big transition point. You must remember that we use the agent as a deep reinforcement learning function, but we like that is always used in this deep reinforcement learning. But whether you are modeling the environment also or not, that basically determines that whether you are having a model free or a model based RL. And by a model of the environment, we mean a function that predicts the state transitions and rewards. So the so from the framework of the reinforcement learning, we have seen that we have states and actions, and the we have the environment. So the if you are also having a function rather than some fixed rules which predict the state transition. So state transition is how to go from one state to the other, and the rewards, then that is basically a model based reinforcement learning. And the main upside to having a model is that it allows the agent to plan by thinking ahead, seeing what would happen for a range of possible choices, and explicitly deciding between its options. So agents can then distill the results from planning ahead into a learned policy. A particular famous example of this approach is Alpha Zero. So this I think is also by DeepMind, which is mastering chess and shogi by self play with a general reinforcement learning algorithm. And a particularly famous example of this is Alpha Zero. So when this works, it can result in substantial improvement in sample efficiency over methods that don't have a model. And the downside is that a ground truth model of the environment is usually not available to the agent. So a lot of times, for example, even in the let's say for our physics based dynamical models, the numerical weather prediction models. We like for if you're talking about simulating the future, we do not know, right, what is the ground truth. We even the ground truth that is being measured by the instruments, the rain gauges, the temperature measurement devices, they also have uncertainty associated to them. So the perfect ground truth is never known to us. And if an agent wants to use a model in this case, it has to learn the model purely from experience, which creates challenges. The biggest challenge is that bias in the model can be exploited by the agent, resulting in an agent which performs well with respect to the learned model, but behaves suboptimally in the real environment. So, agent can perform well in the learned model, but in the real test is actually in the real environment, in the data set which has not been shown to the agent. And model learning is fundamentally hard, so even intense effort, being willing to throw a lots of time and compute as it can fail to pay off. So algorithms which use a model are called model-based methods, and those that don't are called model-free. While model-free methods forego the potential gains in sample efficiency from using a model, they tend to be easier to implement and tune. So you should basically means that, I mean, when you are starting with reinforcement learning, deep reinforcement learning should start with model-free methods. And as of the time of writing this introduction, September 2018, model-free methods are more popular and have been more extensively developed and tested than model-based methods. So, what to learn? Another critical branching point in RL algorithm is the question of what to learn. And the usual suspects are policies. So you have to basically learn the policies, either stochastic or deterministic. Then you have to learn the action value functions, so or the Q functions. This is something that that has to come out from the reinforcement learning algorithm. Or you can learn the value functions or the just the value functions and or the environment model. So based on whether it's a model based reinforcement learning or a model free reinforcement learning, so you will learn the environment model. So these are the other branching points based on what you are trying to learn, and what to learn in a model free reinforcement learning. So there are two main approaches to representing and training agents with model free RL. So the first is policy optimization, and the second is Q learning. So in policy optimization, so methods in this family, so we have seen this one. This is a policy, right? Policy is giving us the probability of the actions given the states. So in policy optimization methods, family of methods, they represent a policy pi, and they optimize the parameters theta directly by gradient descent on the performance of the objective j of pi theta, or indirectly by maximizing local approximation of j pi theta. So this optimization is almost always performed on policy, which means that each update only uses the data collected while acting according to the most recent version of the policy. And policy optimization also, these terms you will frequently come across: the on policy and off policy optimization. So on policy is when you update using the data collected while acting according to the most recent version of the policy. And off policy would basically mean that you are not acting based on the most recent version of the policy. So you're not updating it according to that. And policy optimization also usually involves learning an approximator V phi of S for the on policy value function, which gets used in figuring out how to update the policy. So there are a couple of example of policy optimization methods. So A to C and A3C, which are actor critic methods. So in this case, you have an actor and a critic, just like in GANs we have seen, we have a generator and a discriminator. And we also have this thing known as PPO, which is proximal policy optimization, whose updates indirectly maximize performance by instead maximizing a surrogate objective function, which gives a conservative estimate of how much j of pi theta will change as a result of the update. Now, the second class of model-free reinforcement learning algorithms is called Q-learning. So, which is methods in this family learn an approximator Q theta SA for optimal action value function. So, this is the optimal action value function Q star SA. And typically, they would use the objective function based on the Bellman equations. So, based on the Bellman equation, they are using the objective function, and this optimization is almost always performed off policy, which means that each update can use data collected at any point during training, regardless of how the agent was choosing to explore the environment when the data was obtained. So it's not like the update will happen based on the data which is most recently collected. It can update can happen also based on the data which was collected in the past, and the corresponding policy is obtained via connection between q star and pi star. So this is the actions are given by, so you have to maximize q of theta s comma a, and you maximize this, and arg of max, so this will give you the optimal actions. So there are certain examples of q learning methods known as, so the first is deep q learning, DQN, a classic which substantially launched the field of deep RL. And another is C51, so variant that learns a distribution over return whose expectation is Q star. So then you have other algorithms like DDPG, SAC, and then we have the model based RL. So we will see these in the further classes. So this is actually it will take some time. Deep reinforcement learning, at least we'll try to cover the spinning up OpenAI. So this is like, I don't know, like whether if even if you guys are getting 40 to 50% here is a good thing. Go back and study this material on your own.